Hello, everybody, and I hope you're having a happy Friday afternoon or Saturday evening. And today we are going to analyze and solve problems from the last exam. Maybe we start in a minute so people may join to be with us with the live event. So let's start with problem 1, coin changing. Read the problem quickly. It says, given an unlimited supply of coins of denominations x1, x2 to xn, we wish to make change for a value v that is, we wish to find a set of coins whose total value is v. This may not be possible. For instance, if the denominations are 5 and 10, we can make change for 15, but not for 12. Give a dynamic programming algorithm for the following problem, for which the input is x1 to xn and v. And it is a yes-no problem. Where yes, if it is possible to make change for v using coins of denominations x1 to xn, else output no. So the problem is broken into 4 parts to make it a more smooth solution, and they will complete each other, and we will finally end up with a dynamic programming solution to the problem. So part A had asked, define the entries of your table in words. So the idea, as we had similar dynamic programming problems, is to define a more general problem that can be solved using smaller instances of the same type. What we can use is to have a table T with 2 entries with x1 to xi and the change of value j. So in this subproblem, we assume that we are going to use the first I coins, and we are going to make a change of value j. We can see that we need to solve this problem for j's smaller than or equal to the v, which is the query given in the input, and for I at most n. So this would be the answer to part A, where we have definition of our table. And part B asks, state a recurrence for the entries of your table in terms of smaller subproblems. The reason we defined this table is that we can solve it using smaller instances of it. So one is actually solving parts A and B in their mind simultaneously. And here's the idea. We may use coin xj, we may use coin xi arbitrary number of times. And if we can use it k times, we will make a value equal to k times xi. But the goal is to make a value of j. So j minus k times xi is the remaining value of the change that is going to be made by other coins, because we assume that we are using the last coin k times. So it is going to be made by coins 1 to I minus 1. But we don't know what is k, and any value of k that doesn't make the second entry of the table negative, it can be a valid solution. And if the entry of the table in any such position in this format be true, Tij will be true. So we can write Tij as the OR operator for valid values of k. And by OR, I mean the binary operator of OR, in which if one of these entries in table T be true, be yes, then the value for Tij will be yes. So here we technically have yes to be equivalent to true, and no is going to be equivalent to false in our table. And to be precise, k can be an integer at least 0, and we should only note that k should not make the second term of the table negative. So it should be at most j over xi. So there we have the solution for part B. One may write this as a for loop in which we are going to try multiple different values of k, which is the number of times we have used the last coin number I, or there are multiple notations, and as long as this meaning is represented, it will be correct solution. So we are technically going to see that for loop in the solution to part C, that is asking, write pseudocode for your algorithm to solve this problem. Before going there, we should complete the solution to part B with the initial values, which should be either precisely defined in part A or part B. But it is very important in dynamic programming. So let's first make the definition precise by providing lower bounds for I and j that can be assumed to be 0. We can produce a value of 0 using none of the given coins. So in addition to our recurrence, we are going to have t of 0 and value u is going to be true or yes only if u is equal to 0. And as we can see, the first row of the table for which I is equal to 0 is given in this initialization. And the recurrence can solve can fill the table for values of I greater than or equal to 1. Now we are ready to go to the pseudocode for the problem. So in the first few lines, we have the initialization that is simply equivalent to what we have down there for part B. And next, we are going to fill the rest of the dynamic programming table. So what we do is for being consistent with notation, in the previous loop, we named the variable as j. For the dynamic programming update part, we are going to solve in increasing order of I from 1 to n, which is the number of coins we have. And we are going to solve an increasing order of j. And here we can have a for loop for k, which is the number of times we are going to use the last coin. Assuming that the value of Tij is initially false, this for loop is going to update it correctly. So up to here, we have a correct solution, but it is not optimal in a sense that there is a similar and as simple to this solution way to fill the dynamic programming table, but in less runtime. So let's currently finish this by providing its runtime that is asked for part D. What is happening here is for the initialization, we are running O of V, but for the update, we are taking n times V times the number of iterations for the loop corresponding to k, which can be upper bounded by v. We're taking that much time. But as you can see that in the problem segment, it is explicitly expressed that faster algorithm in O notation is worth more credit. We are going to see a better solution that is similar to this. So this was represented to provide the main idea of the solution. So let's call what we have now an almost correct solution, in the sense that it correctly computes the value, but it's a bit slow. The key observation to make the solution faster is that we don't need to iterate over all values of k and decide that how many times we are using the ith coin right now and go and throwing the xi coin away and going to ti minus 1 and something. What we can do is only make the decision to whether use the ith coin or not. If we are going to use it, we are going to use it at least once, and we can still continue using it. If not, we know that we're not going to use it. So we can throw the coin away and try to make the change of j with I minus 1 coins. So let's write down this idea. So we're going to have a new update that is much faster. So one case is when we are not going to use the ith coin at all. And the other case, we are going to use the ith coins at least once, and we can still continue using it. So the remaining value to be made is j minus xi. So if either of these two cases can work out and be true, we can make the change of j with I coins. One small point is that to note j minus xi should be valid and should be non-negative. So we can make this update into two cases. By separating the cases we cannot use the ith coin at all, which are the cases where j is smaller than xi. But if j is greater or equal to xi, then we can use both cases. So this is going to be the faster update idea for our dynamic programming. And it's going to make our algorithm faster. So let's get to updating the pseudocode using this idea. We can do all in 2 lines by doing an initialization with the case of not using it. Having the second possible scenario if it is valid. .
And we can see that we lost an extra V from the runtime. So there we have the solution to part C, and as part D has asked us to analyze the runtime of our algorithm. The initialization step has only one loop of order V, and the update has two depth to loop of orders N and V respectively. So the total runtime is O of NV. Please feel free to ask possible questions in the chat bar of the stream. We're going to solve problem 2 next. The problem 2, namely majority element, was asking you are given as an input a list of n objects, namely an array A of A1 to AN, where n is a power of 2 for simplicity. In O of 1 time, you can check if two objects are the same or not. We say there is a majority element if there is an element which appears in the list A more than n over 2 times. But that is a definition of majority. And we have an operator to check equality. Give a divide and conquer algorithm to check if there is a majority element, and your algorithm should run in O of n times log of n. One thing is to note that in constant time we can check equality, but the problem explicitly says that we cannot check smaller or greater between two elements. So we cannot, for example, sort the array as a subroutine of our algorithm. So the idea to solve this problem is to do divide and conquer. As it is somehow hinted in the problem statement, so let's look at the array of A1 to AN. The key fact that allows us to do divide and conquer is what I'm writing down.
we can see that the majority element of the whole array remains majority if we split it into two halves in at least one of those two halves, if initially a majority exists. So if it doesn't exist, if there is no element that has appeared more than n/2 times, we don't worry. But if one exists, we can prove that it will be majority in either one of the left or right halves of the array. Let's see why. So assume that AI is majority. Appearing k times in the whole array. K must be larger than n/2. So it is at least n/2 plus 1. Assume that the number of appearances of AI in the left half of the array is KL, and in the right half is K sub R. We must have KL plus KR equal to K. That is larger than n/2. So maximum of KL and KR is going to be at least their average, which is trivial. And using the previous inequality, it is going to be larger than n/4. But note that what is the definition of majority for either the left subarray or the right subarray? Their lengths are equal to n/2. So half of it would be n/4. If one element appears more than n/4 times, it will be majority. And the inequality we have shows that either KL or KR are going to be larger than n/4. So AI is going to be majority either in the left part or the right part. So the fact is proven. Using it to design the divide and conquer solution is easier, in a sense that we assume a majority exists. It is going to be majority of either left or right. we recursively compute the majority of left and right, we will have at most 2 candidates. And we can check them to be the majority of the whole array in linear time. So let's see it. In pseudocode notation. So we are going to define a function MAJ, standing for majority, for an input of size n that is going to return a value that is majority of the array if it exists, or any arbitrary value, or, for example, 0 if it doesn't exist. So it's going to return a value that is majority if the array has a majority. We are going to divide the array into 2 parts. X1 and X2 are the only candidates that can be majority for the whole input array of size n. So we are going to check them. If any of x1 or x2 appeared in the initial array more than over 2 times, it will be the majority, so we can return it as a solution. If none of these 2 cases happens, according to the definition of our function, we can return anything. So let's return 0. One important point that is as important as the whole solution is the stopping criteria for this recursive function. As the solution says that we can assume that the length of the array is 2 to the n, a power of 2. The array size will shrink to 1. So we can check that at the beginning. If n equals to 1, and for this case, we know what the majority is, because there is only one element and it is majority of that array. We will return that element as the majority. So using that, the fact that it proved, it is easy to see why our algorithm is correct. Now let's finish the solution by analyzing its runtime. As we saw for similar divide and conquer solutions, we can have a recursive equation for the runtime cost of our function. So let's T of n be the runtime of our function for an input of size n. This is very similar to what happened to, for example, merge sort algorithm, in a sense that we are using two subroutines of size half there are some lines of the algorithm that take constant time. And there are two subroutines that I implicitly assumed to exist in our language, that is counting a value in an array. But in this problem, we are told that we only have the operator of equality, and counting only requires that. So for the sake of completeness, let me define the subroutine count that takes pointers to an array and a value, and counts the number of occurrences of that value in the array. We can see that the runtime of this subroutine for an input of size n is O of n. And we have two calls to count, which takes asymptotically O of n time. So now we can complete the equation for computing runtime, which is 2 times n over 2 plus O of n. That can be proved by either induction or Master's theorem or other ideas like recursion tree that we have seen in the course. Or one can also cite the merge sort, because the equation is exactly equal to that. The runtime for T is n times log of n. It is worth to mention that this problem has an even faster solution that is linear on the input size, and one can find the majority in O of n, not n log n is required. As some students may be curious of that solution, I would give a hint and by an example. So assume that this is our array. We are going to read from the beginning. We are going to see a 1. The goal is to find a few number of candidates to be majority, and at the end, we will check them to see whether they are majority or not.
So we see one, it may be a majority, there is no reason that it is not. And we continue going on. We see a 3. The point is that majority is defined a number that has appeared more than half of the size of the array. So there can be at most one majority. And here we are seeing two different numbers. At most one of them is majority. If we remove both of these numbers, we have at least lost a non-majority number. So in the remaining of the array, if we already had a majority that could be either 1 or 3, it will remain to exist. And if none of them were majority, then we just remove two non-majority numbers. But if we had seen a 1 again after our previous one, then we could continue because 1 would have been our only candidate. But whenever we see two different numbers, we can remove those two. But we should keep the number of times we are seeing these candidates. This is the main idea that can lead to a solution that through one sweep finds at most two candidates to be the majority and then can check those two numbers to see whether they are majority in O of n. But we didn't get to details of that solution. And the O of n log n solution is what was the target solution for this problem. So let's get to the third problem, which are short answer problems. We will go through them quickly. Part A asks, let omega be e to the power of b times I over 8, and is asking inverse of omega to the power of 5. And we don't read through the all choices, we just get to the correct solution for each problem. It might be helpful to write omega in a notation of e to the 2 pi over 16 times I. And there we can see omega as we had in fast Fourier transform. And for this case, n is equal to 16. It has asked the value of omega to the power of 5. To be inversed.
And using calculus, we can see that it will be equal to omega to the power of 11. Which is choice number B. For part B, again, some simple calculus is asked to be computed. Omega n is e to the power of 2 pi over n times I for some n power of 2 to the k. N equals 2 to the power of k. And it is asking us for which j do we have omega to the power of j being equal to minus omega. It may help to look at the diagram of what happens in the complex plane. So omega n is going to be a point on the unit circle in the sense that if it is divided to n parts. So this angle is going to be 2 pi over n radians. And here we have omega n. And it's going to be a vector space, and minus omega n is going to be the opposite point to the omega n. So knowing that n is power of 2, we can see that, and using the fact that multiplying powers of omega will rotate it along the unit circle, we can see that this point is going to be omega n to the power of n over 2. And if we multiply it by one more omega, we will see that what we want is omega n to the power of n over 2 plus 1. So n over 2 plus 1 is the j we have been looking for, which is choice number B. Let's get to the third problem, problem C, that is giving us a polynomial of this form. And is asking what is a even of x. So as you may recall from the fast Fourier section and how we defined a even and a odd, the terms that are going to make a even are the ones with even power of x. Here, for 1 we have 0, for minus 2 we have a power of 2, and for plus 1 we have a power of 4. And in a even, because all powers of x were even, we divided them by 2 to use it in the divide and conquer. And but the way we define a even is going to give us 1 times x to the power of 0 over 2 minus 2 times
x to the power of 2 over 2 plus 1 times x to the power of 4 over 2, which we can simply write as x minus 2 times x plus x to the power of 2, which is choice number B, again, surprisingly. Getting to problem number D, it is giving us a recurrence T of n equals 4 times T of n over 2 plus O of n, and asking us to solve it. There are multiple ways like recursion tree, induction, and different ideas to solve, but the easiest one would be using Master's theorem. And n to the power of log of 4 in base 2 is going to be n to the power of 2. Comparing it with O of n, we can see that we have the case where the whole runtime is n to the power of 2, which again is choice B. Next, we are going to get to the last problem, part E. Again, giving a recurrence. Here, T of n is 5 times T of n over 4 plus O of n. And similar to previous solution, n to the power of log of 5 over 4 is where the power is strictly larger than 1. And similarly, calculating that the runtime is n to the power of log of 5 base 4, which is again choice number B. So this was the last problem of the exam, and that's it for today. And wish you all a happy weekend. Thank you for watching.